Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. This is lecture number 33 and the topic of the lecture is velocity saturation effects, velocity overshoot and ballistic transport. So, let me first introduce to you what is the concept of drift velocity. Drift velocity is when you apply an electric field. So, this is suppose an electron and the electric field is in this direction, then the force on the electron is along this direction, which is minus q times E. This is the force, because of which there is a drift velocity which is given as mobility into electric field, where mobility is a constant value and electric field is basically E x square plus E y square to square root, which means that this is the effective electric field which is applicable to the charge carriers. Now, just to give you an insight, when you actually go on increasing the force on the charge carriers, it traverses through the silicon barrier or through the silicon lattice, right. It traverses through silicon lattice, and as the electron traverses, there are two forces acting on it. One is the force because of the electric field which tends to make it move forward direction, and there is a scattering phenomena which tends to make it slow down, right. So, when these two forces become equal, the velocity then tends to saturate itself. Now, if the velocity increases, then you can understand that the number of scattering centers will also increase, because per unit time it will hit larger number of charge carriers, and as a result there will be a saturation of the velocity of the charge carriers. So, basically therefore, if you plot voltage drift velocity versus electric field, more so than nature for low values of electric field, this is almost a linear graph. This is almost a linear graph at low electric fields, and I will show you that in my subsequent slides. We define this new term that drift velocity is equals to mobility into electric field, where mobility is assumed to be constant at this stage. Now, if you take silicon, if you take gallium arsenide and germanium, then for mobility for electrons and holes are something like this. Mobility for electrons and for holes, it is 1350, this is 480, this is 8500, this is 400, germanium is 3900 and this is 1900, and these are all the centimeter square per volt second is the unit which is applicable here, right. Now, the total current density due to drift will be given as q times mu n times n plus mu p times p multiplied by E, where n is the number of free electrons, this is the number of free electrons, right, this is the number of holes, right, this is electron mobility, this is hole mobility, and electric field, this is my electric field E, and JD is my current density, drift current density per unit area which you see. And this gives you a brief idea about the basic concept of drift velocity, which means that mobility is an important role which plays in the movement of charge carriers. And though we are assuming mobility to be constant for all practical purposes at low values of electric field, might not be true at relatively high values of electric field. We will see that as we move ahead. I can give you a small problem statement for you to do. So, let us suppose I have a gallium arsenide and it is kept at T equals to obviously at 300 Kelvin, the room temperature. We are assuming that my Na is approximately equals to 0 and Nd is equals to 10 to the power 16 per centimeter cube. Electric field is given as 10 volts per centimeter. You need to find out the current density due to drift velocity. So, this is a small problem I am giving it to you. Please try to solve this problem at least for this condition. You will require some prior knowledge also for this case. Now, let me come back to the velocity saturation effect. The phenomena of velocity saturation generally occurs at very strong inversion when a very strong electric field is applied. So, as I was discussing with you in the previous slide, as you go on increasing the electric field, if you look at this dark line which is the straight line, not the dashed one, but the dark one, then you will see that as the electric field goes on increasing, the velocity increases linearly with respect to each other. So, if you are mobility which is given by drift velocity by electric field, then this is a constant term, because if the increase in Vd is exactly the same as the rate of increase of Ex, the ratio of that will remain constant, which means that the mobility will remain constant. However, as you move ahead and you try to go beyond an electric field known as the critical electric field, which is here, the velocity tends to lower down, or the velocity does not increase as much as is expected. So, this dashed line gives you an idea about how the increase is there. So, the dashed line gives you an idea about, it is almost a linear increase which you see, right, and the dashed line gives you an idea that had it not been these scattering phenomena, I would have actually got the line to be straight. However, because of the scattering phenomenon, the velocity tends to saturate, and therefore, you will see that the mobility tends to change here. So, the mobility becomes a function of the electric field in at least in x direction, if I assume, and tends to saturate at high values. Why? Because the carriers tends to lose large amount of energy through larger interaction with the charge carriers. It is something like this, that if you are moving slowly, you will hit lesser number of people in a crowd, but if you are moving faster, you will also hit larger number of people in the crowd. The idea behind is that if you hit larger number of people, you tend to lose more and more energy per unit time, and your velocity tends to saturate, and that is defined as Vd max, or which is written here Vd max here, means maximum saturation velocity which you get here is Vd max. Now, this Vd max is primarily happening because the reasons I have already discussed with you. We will go into details of this in our later slides as well. Now, at low Ex or a low electric field, as I discussed with you, the drift velocity in the channel varies linearly with the electric field, right, varies linearly with the electric field, which makes that mobility is constant in this case. However, as Ex increases, the drift velocity tends to increase more slowly and approaches the saturation value, which we just now discussed here. Now, therefore, this was the formulation which we used. So, we define an electric field known as Ec, or critical electric field, below which the mobility is almost constant and above which the velocity actually tends to saturate. And Ec is the point where this transition happens, right. Though not a very good picture, but at least for the first go of the subject, this gives you an idea. So, it tells me that when my Ex is less than Ec, my Vd is almost mu times Ex, right, and that gives you the value. When Ex is much larger than Ec, then Vd is exactly equals to Vd max, which means that the maximum saturation velocity has been reached. Therefore, we define the critical velocity as Vd max by mu, right. Mu is the mobility of the charge carriers. Now, electron velocity and hole velocity are given here, given at these points. Please understand that the velocity will be different for a bulk and for interface, which means that the electron is moving in a bulk silicon without any impurity, without any interface traps. Its mobility will be relatively higher as compared to when the mobility is moving in the interface, which typically happens in a MOSFET. In a MOSFET, the electrons are actually moving through the interface between silicon and silicon dioxide, and that is the reason there will be heavy scattering and the mobility will sharply found out. So, we define two types of mobility. One is low field mobility mu 0, and then we have an enhanced mobility which is mu e, right. Also, we define towards mu bulk, which is bulk mobility, and this bulk mobility is almost equals to the low field mobility in this case. The simple velocity model is applicable for the electric field model, and you can write down here that the Vd, the actual value of Vd is Vd max upon Ex by Ec upon 1 plus Ex by Ec. Quite interestingly, when Ex becomes equals to Ec, then you see that this value will be approximately equals to 1, this will be equals to 1. So, you will have Vd equals to Vd max by 2. So, at critical electric field at Ec, the drift velocity is almost half the maximum velocity, and just after this it reaches to the critical velocity. And we are assuming for all practical purposes that all the current flowing through the device is because of drift, there is no diffusion component attached to it. And we have already seen in our previous discussion that the magnitude of the longitudinal electric field, longitudinal means from source to drain, this is longitudinal electric field, is given by d psi s dx, which means the rate of change of surface potential with respect to x, if I assume this to be as my x direction, right. If this happens to be my x direction, then this direction is Ex electric field, and this direction is epsilon s or psi s, which psi s is basically the surface potential along this direction. Now, so with this knowledge or with this idea, what we can do here is that we will be actually now coming to the concept of Ex. So, if you see at Ex, which is basically, so this is Ex as a function of x. Quite interestingly, the electric field is also not constant with respect to x as one moves along. And I will give an example for that in case if you have missed the previous discussions, that in a MOSFET, if you plot x versus say psi s, right, the surface potential, this is my source end and this is my drain side and this is my channel length, right. Then at the source end the surface potential will be equals to V built in, and at the drain end it will be V built in plus VDS, and the movement how the potential takes place is something like this. It is somewhere in the middle it becomes minimum and then it increases, and the increase is much faster or much larger towards the drain end. At the drain end the increase is so let me put this drain value here. At the drain end the increase is much larger and the source end it is almost flat, which effectively means that the rate of change of potential with respect to x is much larger towards the drain side, right, and that makes the electric field also very large on the drain side. And that is the reason if you see carefully Ex is written actually as a function of C. Therefore, at any point x we can write down my Vd to be equals to Vd max times 1 by Ec into dVcb dx here 1 by Ec, right. And as you can appreciate that when Ec becomes very large, right, I can neglect this and this because they become, so this what will happen is that if this becomes, or let me say that 1 by Ec becomes therefore very small, I can neglect this with respect to 1, I can neglect this with respect to 1, and what I get is Vd equals to Vds max. This is the case when your Ec is very large. So, when your critical electric field is relatively very large, obviously your drift velocity becomes almost equals to the maximum velocity of the charge carriers, right. And this is 1 by Ec which you get, it is 1 by Ec means the critical electric field. This critical electric field is again a function of many other quantities, but at this stage we are assuming this to be almost constant at this stage, and we will move ahead. And therefore, we write down Vd, because you see what we have done is that we have now Vd max by Ec will be given by mobility. Mobility is already V equals to mu into E, and therefore, what we have done is that Vd equals to mu times dVcb dx into 1 plus 1 by Ec dVcb dx, which means that very critical is basically the rate of change of the channel potential with respect to bulk, right. Channel potential with respect to bulk is Vcb. So, if dVcb dx is very large, right, then typically the electric field is very large, Ex is very large. Look at the right hand side diagram here, and as you can see this is for Id versus for Vd, and as you can see here that for short channel devices the currents are relatively small, and you do have for long channel devices the currents to be relatively large for the same value of VGVD. Now, if you assume that there is a velocity saturation, so how did you define current from your basic idea? The drain current depends upon the drift velocity. Higher the drift velocity, more will be the drain current, if everything else remains constant. So, if you look at this expression IDS with velocity saturation is given by IDS without velocity saturation divided by 1 by VDS upon, so VDS by L of EC. L is the effective channel length which we get 1 plus, this is effective scattering voltage which we get here. So, this is 1 by VDS upon LEC which we do. Now, if I assume to be strong inversion, and then the effect of velocity saturation is small, as for if it is a moderate inversion or very weak inversion, then velocity saturation component is very small, as the current is primarily diffusion dominated, whereas in strong inversion it is drift dominated. Now, actually the drift diffusion model, DD model, fails at very short channel, ultra short channel devices, where there is a very high field or there is a rapid variation of the potential present within the channel, which means that the rate of change of potential with respect to space becomes so large that my drift diffusion model tends to fail. Now, in this case we can say that the scattering event is not only localized at particular domain, right, is no longer domain, but it is spread across the whole channel, and the carriers can acquire much larger velocity than the thermal energy over a portion of device. So, which means that for a very short duration of time, your output velocity of the charge carriers can actually overshoot or become much larger than the thermal energy required to have that velocity, and this is defined as the velocity overshoot. However, these carriers will not be in thermal equilibrium with the silicon lattice and referred to as hot carriers, because it does not get enough time or enough scattering events to relieve its energy to the lattice, and therefore, they are almost held constant. Therefore, it is possible for the charge carriers to overshoot the saturation velocity, and this phenomena is referred to as velocity saturation. You remember what was the concept of velocity saturation? The concept of velocity saturation was that when the electric field tends to make the velocity high, the drag also increases, which means the scattering event increases. When they are equal, we say define that to be as the saturation, but in reality velocity can go beyond that and is defined as the velocity overshoot. Let me come to the last phenomena which we were supposed to discuss, and I am keeping it very qualitative in nature at this stage. It is known as ballistic transport. Now, till now the limiting factor for any velocity in a semiconductor is basically the scattering event. So, higher the scattering event, more will be the velocity limitation happening. Now, the average drift velocity, if you see average drift velocity, obviously is the function of the mean time between the collision or the mean distance between scattering event. If the mean distance between the scattering event is lowered, I will have larger number of scattering per unit time, and as a result my velocity will be almost getting constant. However, this happens in a long channel device, right, and this what will happen is that when you do have a long channel device and the mean time or the mean distance between the collisions are very small, then it is a collision dominated or scattering event dominated phenomena. However, for very short channel devices, ultra short channel devices, if going from one end of the source to drain you enter into just say 3 scattering event or just 4 scattering event, then we define that to be as this ballistic transport. Ideally, ballistic transport effectively means that one can go from source to drain without scattering event, effectively meaning that the mean distance between scattering event is of the order of the channel length. If that happens, we define that to be as the ballistic transport in case of a ultra short channel device, right. So, in a ballistic transport, as you can see here, that if the channel length is further reduced, means it is reduced below that L value, where L is the scattering length, then a large fraction of carriers actually could travel from source to drain without experiencing any scattering event, which means that there is no scattering, which means that the mobility is always held constant, right. You will always, there will be scattering event, but the velocity will be much larger. So, if you look at the left hand side graph here, this plots ID versus VD for various values of Vg. You see, as the Vg value goes on increasing, the dotted curve current is much larger as compared to the blue curve currents, right, and that this is 5 volts, and if you look at this 5 volts here, this is constant mobility, right, because there is no scattering phenomena, and you can see you get a jump in terms of the current. Now, since the carriers travel faster than the average drift velocity of the saturation velocity, this could actually have very fast devices. Ballistic transport occur in those devices very short channel lengths, right, and this gives you a brief idea about what ballistic transport meaning. So, there are many devices on which many devices or many researchers working on it, where ballistic transports have been used to showcase a larger current in a device, especially in very short channel devices, right. So, what we learned here, this is a brief of the what we have learned. We learned about the velocity model, we learned about the velocity saturation model, velocity saturation. We learned about overshoot, velocity overshoot, overshoot, and then we went ahead and did mobility versus electric field graph. Then finally, we worked on the mobility versus electric field, velocity overshoot, VD saturation, and then we worked on the values of the last one was ballistic transport, right, ballistic transport. It is a topic of research which is going on, and people are working on it, on the ballistic transport, how to make the ballistic transport work properly. So, these are the few domain areas where people are working still. Let me come to now the mobility effect. Now, I was explaining to you the concept of mobility was equals to that. How did you define mobility? Was that my drift velocity was equals to mobility multiplied by electric field, and where mobility was coming in current. If you plot current, it is mu times Cox, if it is an N type, into W by L into Vgs minus Vth whole square. This is Vgs minus Vth whole square, which is saturation. And we say that mobility is constant, and therefore, we say that this quantity is whole constant, it only depends on the value of Vgs, but not in reality. What we will see now is that this mobility, which we were assuming it to be held constant, is in reality not so. Its value goes on varying with respect to this. So, what we will do is we will look into the various causes of mobility degradation, or what is the change in the mobility. We will also look into scattering mechanisms, for example, lattice scattering, ionized impurity scattering, surface roughness, Coulombic. These 4 we will be looking in detail, but just for in carrier scattering and remote Coulomb scattering, we are just giving the name in this case. We have already learned the mobility effect, and basically the definition of mobility is the measure of how quickly the charge carriers can move through a semiconductor when electric field is applied, and therefore, we already know its value. This is where we define this to be as a low field mobility constant slope, and this is where we define the high electric field. So, we are plotting carrier velocity with respect to electric field mobility. If you therefore see the cross here and here, this part is my critical electric field, which is my EC, correct. So, these are the basic things which we already in a sense have done it in this course of action as mobility effect. Let us come to the mobility degradation. I will try to explain to you first from the physics of the device and then from the mathematics. So, you see, in simple silicon dioxide interface, if you have, this is my silicon dioxide interface, this is oxide and this is my metal, and this is my silicon here, and when you apply a positive bias here, then Ey, if I assuming Ey to be the electric field in this direction, Ey goes on increasing, right, Ey goes on increasing. As the Ey goes on increasing, the electrons from the substrate tends to gravitate towards the silicon dioxide. This is my silicon dioxide interface. Right. Now, as the vertical electric field increases, as the dimension reduces, if you follow the scaling theory, then everything, the voltage also reduces, but Tox reduces. When Tox reduces, the value of electric field goes on increasing, and when it goes on increasing, it effectively means that the electrons or holes, whatever be the carriers, are pulled very close to the silicon dioxide interface. Now, understand, this silicon dioxide interface is not a very good interface. It has got large scattering centers available. Why? Because, say for example, some oxide, some silicon did not get fully oxidized, so there will be some dangling bonds there. There will be interface trap charges, there will be also oxide trap charges. So, those trap charges are primarily responsible, are sort of scattering points. So, when the electron starts to move from source to drain, these scattering points are the points where the electrons get hit, and as a result its effective velocity reduces and the mobility tends to reduce down, and that is the reason it is known as a mobility degradation, right. So, with increasing electric field the mobility actually starts to degrade, and it is given by the formula which is shown here this particular point, that mu effective is equals to mu 0 into 1 divided by 1 plus theta times Vgs minus Vth. Vgs minus Vth is basically defined as the overdrive, right, and mu 0 is the low field mobility or bulk mobility, right. Mu effective is the effective field mobility. So, theta is a mobility reduction factor. Higher the value of Vgs minus Vth, lower will be the value of effective mobility, right. And as you can see here on the last point, that as in the short channel, as the lateral electric field increases, the channel mobility becomes field dependent and eventually velocity saturation will occur. Now, if you look at the temperature dependency of mobility, then quite interestingly, if you plot look at this diagram here on the top right corner of your screen, it is basically plotting log of mobility versus temperature, 1 by temperature. This is 1 by temperature which is being shown here. So, when your temperature is very low, so let me just give you a brief idea about this particular point. When the temperature is very low, it is impurity scattering dominated mobility degradation, and when the temperature rises, it is lattice or a phonon scattering limited mobility. Now, why does mobility decreases with increasing temperature? Well, it is very simple and straightforward. If you actually increase the temperature, you tend to make the scattering center shift back and forth about its mean position, and therefore the probability of scattering becomes larger, and that is the reason the mobility falls down, right. So, that is the reason if you look carefully, if you plot it, it looks like as the temperature increases the effective mobility goes on reducing, because it is 1 by T which is shown here, and the relationship is given as mu is proportional to T to the power minus m. And if you look at there will be a point where the mobility will be maximum at a particular temperature, right, and will go down as you move away from that temperature to the right or to the left. To the left, why? Because of something which is known as impurity scattering, to the right because of lattice scattering, and both will give you the mobility effect in a sense. So, these are the scattering mechanisms which are primarily responsible for the charge carrier movement, and these are lattice scattering, ionized impurity scattering, surface roughness scattering, Coulombic scattering, and carrier scattering and remote scattering. Let's come to first of lattice scattering. As I discussed with you, a carrier moving through a crystal is scattered by a vibration of the lattice because of resulting from the temperature, and as the temperature increases, the frequency of collision becomes larger, mobility goes down, right. And therefore, the phonon scattering limits mobility as the temperature increases. As you can see here, this is the defect scattering, this is Coulombic scattering which you see, and this is the lattice scattering or electron lattice scattering which you see, and this is boundary scattering is the edge of the device, where the edge of the interconnect where you are putting it, that is defined as the boundary scattering. This is known as the lattice vibration. So, lattice points of silicon will actually vibrate about its mean position, and there will be scattering because of that. There can be any defect. For example, when you are doing a silicon dioxide, let us suppose one of the lattice atom is missing, right. There might be diffraction or there might be an interaction scattering mechanism because of that. This is known as a defect scattering induced mobility degradation. So, these are the few phenomena which happens when you do a lattice scattering based design. Let us look at ionized impurity scattering, very simple and straightforward, that if you are basically say doping with boron or even arsenic atoms for making it 3 type or an N type, and then you let the electron pass through, there will be a repulsive electron repulsive force or even an attractive force like this, because of which the direction of the electron in this case and the direction of electron in this case will go on changing. Now, however, there is a problem here, that if the electron is moving slowly towards the boron atom, there will be more change in the direction. So, less is the velocity of the charge carriers, less the velocity is, more will be the change, a more change will be expected. However, if velocity is more, then the change will be relatively less, and the reason being, if the velocity is more, the interaction will be much minimized, the time of interaction will be much minimized, and the direction of change will be therefore less. As you can see here, impurity scattering limited mobility is T to the power 3 by 2. As the temperature goes on increasing, the mobility tends to increase in this case. Try to find out the reason why it is happening. And the reason it is happening is that both the carriers and the atoms are moving very rapidly. Let me come to surface roughness scattering, and this is due to surface irregularities which is happening. And this surface irregularity is again charge scattering based, surface roughening scattering based, and remote surface roughness based. What is charge scattering? So, let us suppose I have surface roughness, which means that there is a physical roughness of the surface, right, and therefore, there will be heavy collisions taking place here, and there can be also a remote surface roughness which will be occurring. If you look at this particular point, then I have got the source region and the drain region here. The charge carriers are moving here. This is a boundary collision which is happening here, this green colored one, because of which you will have effective path of the charge carriers becomes larger and the mobility drops down. Now, surface roughness scattering defines the impact of the roughness of the silicon dioxide interface, right, and that primarily is the surface roughness scattering. This is the physical surface roughness which tends to make the mobility lower. Now, remote surface roughness is basically the surface roughness. Gate metal surface roughness means the surface here will also influence the mobility of the charge carriers, right. And this gives you a brief impact of the surface roughness scattering, the origin of those roughness scattering, and how does it influence the mobility of the charge carriers. We will take up the next section in the next lecture, and where we will be further defining the other parameters of scattering, and then we will finally end this series on reliability issues typically in a MOSFET. Thank you.